If audible, फिर कोई problem नहीं. Now we started. Okay, as per your demand, as per you told ki sir, ray optics will revise. It's fine. Maybe tomorrow, maybe at the end if you are left with time. But sir, now start the fresh topic, that is wave optics. So students, here we are with the fresh topic, that is wave optics on your screens. I hope it's clearly visible there, isn't it? Just focus there on the screen. Okay, it's visible now. And we have started all the things here. So you can see on the YouTube also your videos there. Okay. Recording is already started. Don't worry. Recording is already started, students. Okay, don't worry about that. Okay. So I'm closing this video. Yes. So now be focused here on the slides. Okay. Be focused here on the slides. So just one thing, wave optics. So write the heading in your notes, fresh topic. This is wave optics, students. Write the heading in your notes, a fresh topic. This is, that is wave optics. Voice is lagging. What's the issue? Now I think it's fine. Now I think the voice is fine. After that, we'll study the interference. After that, we'll go through the diffraction and then polarization. So this is all about the wave optics. Write it down in your notes. See what happens if you want to write some book. Okay, if the contents are good, so it looks good when reading the book. So similarly, make your notes such that it's like a book for you. Okay, like your self-made book, and you are the author of this book. Okay, of course, it's sure that you are copying the things, but if you're writing like this, it will be very interesting for you. Your notes for yourself will be interesting. So next time when you want to revise the things, it will be very good for you. Okay, so make the notes in such a manner. Write these things in your contents fast. If you have written, please reply in the chat box. If you have written these things, please reply in the chat box. Okay. Okay, so let us start it. See, first let us go through the history. First, let us go through the history. Okay, so one more student have joined. Welcome to today's class. Fine. Okay, so let us go through the history first. So what happened in 1637? What happened? So nothing happened. See, we'll see what happened now on the screens. So see, there was one scientist whose name was Descartes. Okay, so what he did, he given a model which is known as Corpuscle model of light. Okay, and according to this model, what happened? He treated light as what? Light as a particles of energy, corpuscles of energy or particles of energy. Okay, so what he given, his name was Descartes. He's given a light as what? He treated light to be like corpuscle. Okay, I mean packet of energy. Okay, like a particles or the packets of energy. This was in 1637. Remember, we are just talking about the history of light. Okay, so let us wait. Let me see on the YouTube what is happening there. Okay, so next what happened? According to this, it derived the Snell's law also. Okay, so we know this thing that suppose this is a reflecting surface. We have seen this thing in the reflection chapter. As it is on your screen, we have seen this thing in the reflection chapter. Okay, what used to happen in that we were treating the light as what? Students, if you see there, how we were treating the light there? Light was treated as ray there. Okay, so it was coming like this on the surface, it was meeting, and then it got reflected there. Fine, this was the ray theory. But now if you see here, hold on. But now if we see here this Descartes, according to Descartes, he's saying us what? He's telling us like this: treat the light to be like the corpuscles, like the energy packets. You know, you have seen that animation Dragon Ball Z. He was having his corpuscle there. Okay, in that he used to be. If you have seen the animation, you'll be able to know something known as like a particle, like a kind of spaceship which is like in a globe shape, and it is like full of energy. So such corpuscles of energy, light was treated as like this according to Descartes. And then he did what? He treated like this, that this incident corpuscles are falling on a reflecting surface, and this is the point of incidence, and they are getting reflected like this in such a manner that again this corpuscles of particles are getting reflected away. Dun, 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 dun. Okay, this is incident corpuscles, these are reflected corpuscles, and this at this point this is known as normal to the reflecting surface. This we have seen already. What we are doing is this: in the reflection chapter we have seen reflection, the same phenomena, by treating light as a ray. But according to this wave optics, as per the history of the 1637 Corpuscle's theory was given by Descartes, he treated that if you treat that phenomenon of reflection, which is as a ray, light as a ray, but now it is as a corpuscles of particles, you will get this picture in front of you. Till here, I hope it's understood. Now what happened? If you see the refraction process also, this was what? This we are seeing the reflection process as corpuscle model. If you treat the light to be corpuscles of energy or particles of energy. But now, if you see the refraction process, we have just, I mean, this also we have seen in ray optics chapter. Hai na? If you see the refraction process, by treating light as corpus, according to the corpuscle model, we can see these energy particles are going like this. So when the ray goes from a rarer medium, which is having a lesser refractive index as compared to the denser medium, it bends towards the normal. So similarly, what happens when this light particles, I mean the corpuscle model of light, corpuscles of energy, particles are passing like this from one medium to another medium via a boundary which is separating two mediums. You can see they are also bending. Is it fine? So both the things were symmetric. This is just the history, you know, to create the interest. I mean, so we can go in the history and like you can connect all the things, like connecting the dots back when we are farther away in the slides. Okay, in the future. This was a recent history. Till here, is it clear? Please reply in the chat box, yes or no. Students, please reply in the chat box, yes or no, if is it clear. Okay, I hope it's clear. Okay. If you are not replying, I assume this is clear for you. Let me see the YouTube students what they are doing. Please reply. Please reply. If you not reply, how will I be able to know? Okay, it's going on. Very good. Okay, so now let us see. Yes, very good. JNBDIU students, excellent. So you're focused. Very good. So now let us see. See, after 1637, that is corpuscle model of light was shown by Descartes. See, always by connecting these things, we are respecting the scientist. I mean, you know, one more thing is that if you remember the history, everything will be very smooth in our brain. You know, we can connect the things. Then what happened in 1672? After some years, one more scientist, very famous, is known as father of Newtonian mechanics. He founded what? Classical mechanics. He's known as the father of, Newtonian mechanics. Classical mechanics. In 1672, okay, he did some work on optics also. He did the work in the optics field. So he was very multi-talented, I tell you. Isaac Newton, okay. He did work in the field of optics also. And he founded what is known as corpuscular model of light. He worked on this. See, Descartes gives you somewhat of the corpuscles, but he actually worked on that, and he told like this, and he published a paper in German. It's French, and it was written like this: optics or a treatise of the reflections, refractions, infections and colors, all these things. Okay. So what he told is like this. Okay, I'll give you a little bit information of corpuscle model of light, which is modified model of the initial corpuscle model of light, which is given by Descartes by Isaac Newton. He told like this, but suppose we are having dispersion process. Students, we see the dispersion, know how the dispersion happens. I hope all of you know this thing. How the dispersion happens. I mean, suppose white light is passing from prism, you are able to see the 7 colors. This 7 colors you can also see in the thin film interference. What happens in the Descartes? What he found is this thing. Descartes was not able to give the proper explanation of this thing, 7 colors. But Isaac Newton, through his corpuscle model of light, has given explanation of the 7 colors. He told like this, that for each color, say red, it's like the light like this, no, Wib, Gior. So he told like this, for the red, yellow, orange, yellow, green, blue, indigo, violet, for all these colors, there is different particles or corpuscles, particles of energy of the same color. That is, for the red, it will be red color. For the orange, it will be orange. For the yellow, it will be yellow. Okay. For the green, it will be green. For the blue, it will be blue. For indigo, it will be indigo. Okay. And for violet, it will be of what? Violet color. So for each of the colors, particles of energy will be what kind of? Their own. Okay. I mean, it's in synchronized with it. Okay. It's same color. So after this was in 1637. This was in 1672. So after this, what happened? In the year 1678, Christian Huygens, okay, he has given what? Christian Huygens. Somewhere like you can pronounce it as like Huygens, but Huygens is the proper pronunciation. Okay. In 1678, Christian Huygens, what he did? He has given the wave theory. So students, we studied in the dual nature. You will study in the future actually. There is something known as dual nature of light. That light for some experiments behave as a particle, and light for some experiments behave as like what? Wave. Okay. So in the initial 2 years, I mean, in the history, if we see the history in 1637, Descartes has given that light is what? It's like a corpuscle, like particle. Precisely particles of energy or energy particles. Then Newton in 1672 in his optics paper in journal he published, in that he is given like this, that he modified this theory more. Okay. And he have explained all the phenomena like reflection, refraction, dispersion also via prism, and that is light into 7 colors via this modified corpuscular model of light. Okay, this was given by Isaac Newton, or you can say Isaac Newton. This was given by Isaac Newton. Okay. Then in 1678, after a few years, here comes the hero, that is Christian Huygens. He is given wave theory of light. Now it was a contradiction. I mean, somewhere the people are treating light as the particles. Somewhere the people are treating, I mean, the scientists are basically treating the light as a wave. So now we'll start our chapter, that is wave optics. Okay. With this scientist, that is Christian Huygens or Huygens, and he have told like this, this is a wave theory, and this is our chapter, that is wave optics. And the history starts from this point of our chapter, that is today's topic, wave optics. Okay. So see, in 1678, when this Christian Huygens given this thing, Huygens, when he has given this thing, that is wave theory, then in 1801, Thomas Young also did some experiments. He was also a very famous scientist in the times of all the scientists. Okay, so let me write the name. Started from the Descartes, then our Isaac Newton, and then what? Christian Huygens. Then in 1801, Thomas Young, okay, he was also a very famous scientist. He did a lot of work in optics, and he founded what? He has given his own wave theory of light. Okay, and you will find that we'll see diffraction experiments which are being explained by this scientist, which is known as, you know it on this, it's on the screen, Thomas Young. He did interference experiments. Okay, double slit interference and all these things. We'll see all these things in this chapter. We'll understand what is interference, what is diffraction, all these things. Diffraction, okay? So let us see first the failures of Newton's corpuscle theory. So Newton's assumed that the light travels faster in the denser medium. If you focus here, see on the slides, Newton assumed like this, and that the light travels faster in the denser medium than in the rarer medium, which has been proved wrong. You know this thing. Anna, let us see it in a more depth. So corpuscle theory cannot explain the phenomenon of diffraction and interference and polarization of light. These are some points. So write in your notes, okay? I'm erasing this all. So just hold on, students. If you see the first point, that Newton assumed it, that it travels fast in the denser medium, which is actually wrong. So this was a failure. Second failure was this, that his modified theory of corpuscular, okay, particles of energy of light was not able to explain the phenomena of diffraction, interference, and polarization. Students, have patience. This we'll see afterwards, not now, okay? This and these three processes, what are these? Got it? These three processes we'll talk afterwards, not now. Then comes, okay, write these things first. I've given you the time, write this thing. You can write this page. I'm moving back. Write somewhat about the history. It's all on your screens. By the way, you can see it yourself. Okay, I write this. You wanted a time to write, na? Write like this history, somewhat this page, then failures. So reply in the chat box if you understood and if you want me to proceed for the next slides. If you want me to proceed for the next slides, please reply in the chat box. I'm waiting here, okay? Please reply in the chat box. Students, you are not replying. How are you able to get to know this thing that you understood it and you've written? Okay. Okay, I'm moving next. Okay, and I'm moving towards the next slide. So see now, it will be very smooth. So these were the failures which I have already explained you. Fine. Okay. See, in the geometrical optics, we have seen this spectra in the beginning. I hope from you, okay, that this is nothing but the visible region spectra, visible region. Okay, I'm gonna try like this, Vib, Gior. Okay. Okay, DU students are seeing previous slide. So here is a previous slide on your screen. Previous slide is on your screen, students. See, actually we know that suppose there is a denser medium. I'm explaining the first point here. And this is rarer medium. Okay. And suppose the light ray is traveling like this. Suppose from a denser to a rarer medium. We know according to the Snell's law of refraction that the speed will increase here. And if it is V1 here and if it is V2 here, V2 will be greater than V1 in the rarer medium. But Newton assumed this thing during when he was giving this Newton's corpuscular theory of light. He assumed like this, that light travels faster in a denser medium, which is wrong here. As per geometrical optics, we have seen in the Snell's law of refraction, not reflection, but refraction. देखा था ना ये thing, है ना? So same thing as this. Is it fine, students? First point is explained here. Second is simple. When you will understand diffraction process, interference and polarization, you will get it. Yes, this how corpuscular theory is not able to explain these phenomenons. Clear? Let us move next. So this was in the geometrical optics, visible region spectra, that is VIBGYOR. See, we see the wavelength of the visible light. We know we treated in the geometrical optics that the wavelength of the visible light, or the light which we are using for the optical phenomena, as per the geometrical optics law, they must have the dimensions of the typical mirrors and lenses say be very, very less. Lambda of them must be very, very less. Okay. So according to this, we can say light can be assumed to be approximately travel in straight lines. This was assumed. This was the conclusion of this point, by the way. But if we say that lambda must be less than the dimension of the mirrors and the lenses, it means it has to be treated as like it is traveling in a straight line. There is no curve there. Okay. So see, there is a picture in front of you. If you are seeing this candle, this lighten up candle via this kind of thing, how much picture you want? Write it fast. Okay. See, PDF will be given to you. No, why do you worry? PDF notes will be provided. No. Tomorrow students will revise ray optics. Okay. Otherwise you people will forget. Tomorrow we'll revise ray optics. As to aapki demand, according to your demand, we have done this thing. Okay. See, DIU students and all the students who texted here to be like, it's slide ke liye, please note it down fast. Okay. Okay, now let us move. Okay. So if you focus on this candle and this candle, and see, if you focus from this, so we can see this thing. Hold on. As if you see this, will you be able to see this thing? And if you see like a curved, how will you be able to see? Just observe, students. Are you able to get this thing? See, the light rays travels in a straight line. So here the chances are there so much that we'll say we are able to see the candle. And if you see from here, light ray will go inside. If there is no any reflecting surface on the edges, light can't reflect and come into the eyes. So it is the rays which is coming into our eyes, due to which we are able to see the objects or the sources from which the light, source object or from which the light is coming. Source object from where the light is coming. Here you will see that the light is traveling straight direction. And in this you will see how the light is traveling. You can see here. Okay. So I will say here the chances are less, but here it's more. Fine, students? It's very easy. Here the chances are very much. Here the chances are very less. Sad smile, no smile. Okay. So in this niche wala, we may not be able to see the image. Next. If you focus here, this is what? Again, back to our previous slides, but some changes here. So this derivation, I mean, this conclusion of the point that light can be assumed to be approximately travel in straight lines. This is according to geometrical optics. I mean, if there is some source of light, say some Diwali Deepak kind of, I mean, you know, like this. So light will be coming from it like this, like this, like this, like this. And it must travel. We assume it is traveling in the rays and in the straight line manner. Next come the wave optics. So as per the wave optics, students, we say here size of obstacle and the path of the light is in order of the wavelength of the light. Okay. Suppose, let me tell you. So it says that light does not travel in the straight line. This is according to our today's chapter topic, that is wave optics. So it is in contradiction, or you can say not a contradiction properly. I can say like this: it is like anti to geometrical optics. Why anti or opposite? It gives an opposite sense. Why it is? Because the conclusion of the previous slide, that is from the previous chapter, basically, that is geometrical optics, we have concluded this thing that light can be assumed to be approximately travel in straight line. Okay. But if you see here, that is in the next slide, that is wave optics slide. Here, the law which is working for this conclusion is this, that if the light is going like this, and there is some obstacle in between, so the light will bend around the edges, which is basically known as, in the lower classes, you have seen this thing, it's diffraction process. And from this, if it is bending around the edges, we can conclude light doesn't travel in straight line, which is opposite to the previous conclusion. Is this point clear? Yes or no? See this thing. These are the light rays. You can treat like this. These are the light rays. These are getting bending. These are getting bended around the edges of this obstacle. This is obstacle. And around the edges, light rays getting what? Bended. And this process is known as diffraction. This process is known as diffraction, students. This process, students, is known as diffraction. Is it clear? Yes or no? Reply fast. Students, reply in the chat box. Okay, one of you have replied. Okay, JNVDIU student says yes, cool. Now let us move toward the next. So we can say that according to this wave optics thing, that if the size of the obstacle in the path of the light is in order of the wavelength of the light, so this can be concluded, and this is from the wave optics. Now comes the Hygens theory or Hygens theory. Write in your notebooks. Students, now we are going to study history is completed. History is made, students. History is done now. It's done. Okay. I haven't drawn a good like here, so I must erase it. History done. Check. Now write this heading, Hygens theory. What do you say? Okay. So hold on one second. Let me see this thing. Students will study this thing. Okay, write the contents of this theory. Okay, write the contents. Write the contents fast. I'm giving you time, and if you have written, reply in the chat box so I can move next. Okay. So I can move next. Reply fast. Okay, don't waste time there. Don't waste time, students. Reply fast. I think the contents is not visible properly. Let me show you this thing. Okay, these are the contents of Hygens theory. Please write on this. Okay. Write that, students. If you've written the contents, please reply in the chat box so that I can. All of you must try it. Now the chapter actually starts. Okay, students. Chapter has started it now. I want all of your replies. Until and unless if you don't reply, it doesn't make sense. Otherwise, why we are we are working hard. I mean, you people. I'm telling about you. You are coming in the afternoon and attending the classes. It takes the efforts, energy, time, data, everything. So it must be worth, no? Useless nahi jana chahiye na. That's the point. Okay. So please, all of you reply in the chat box if this is fine, so we can now start it soon. Fast reply it. Anybody replied? Okay, only one students have replied. What about other GNB students? I want everybody's reply. I want to see how many of you are alert. I want to see, students, how many of you are alert here. Okay. Otherwise, what's the use? Please reply it here. Yes, good. What about other students? I want everybody's reply here. What about other students? Reply, everyone. Reply fast. I'm waiting for your replies. Okay, few 2-3 JNVs are remaining. Reply fast. I want to see that are you with the class, with the pace, or like sleeping? Otherwise, what the use? Anna, reply fast. Okay, clear. So students, it's fine. All of you have replied. Now let us proceed. So now we're going to proceed. Just wait. Okay. So students, now it's a time to revise. Okay. So contents likely tomorrow we'll start with the contents wavefronts. Okay, let me show you first animation first. Okay. So एक animation देख लो. Don't create disturbance in the class. Okay. Jinmi Changling students have done. So see this animation of the wavefront. Then we'll revise 15 minutes for the ray optics, because ray optics revision also required. See this, what is happening? You can see this in this video. Water is falling from the tap drop by drop. Tap, tap. It's falling like this, and you can see how the wavefront is produced. And this is the side view of the same picture. Waves are produced on this. This is the side view. Okay. See this. So what is wavefront? Wavefront is actually the locus of all these points. It's drawn here. Locus of all these points is basically wavefront. That is circular shape. So suppose you throw a stone in the pond. From center, the vibrations will set up and down, and circular kind of vibrations or wavefronts will be produced concentric with each other and having the radius in increment. So such locus of all these points which are in the same phase If I draw it, it will be circular shaped for this case, and this is known as wavefronts. This is known as what, students? This is known as wavefronts. ठीक है, लिख लिया? Fine. So we'll say locus of all the points. Students, don't make noise. The locus of all the points which oscillate in the same phase is called wavefront. So these are the wavefronts. This is all having concentricity, radius R1, radius R2, radius R3. And what does it mean by constant phase? Remember, iska kya matlab? What does it mean having the same phase? It means if you see all this circular, if you focus on the all of the circular tracks, and on all of the circular track, there will be many of the number of the particles. Many number of particles. You can take the smaller radius also, but I am taking here this. There will be many number of particles here. Okay, and all these particles either oscillate up or oscillate down, plus minus 0, plus 0 minus 0 plus. So when they are on the same phase, it means if one is plus in the same circular track, I'm saying, okay, just focus on the individual circular tracks having radius R1, R2, R3. If you're saying it's R3, if one is up, next will be up. If one is down, next will be down. It's not like this. There is not a gap in up and down motion of the vibrations on a particular circular track. Got it? This means same phase for every of the particles on individual continuous particles on the individual circles. This is known as wavefront, and the light rays always travel in the perpendicular direction to the wavefront. I mean, wave will be traveling like this perpendicular direction to the wavefront. Okay? So students, this was all about the wavefront here. Now, the speed, if someone asks from you that what is the speed with which the waves are traveling, suppose you put a stone in the pond and wavefronts will be generated, vibration will be circular. So what is the energy wave direction, wave energy direction, or the wave speed basically? What is it? You will say it is given by with which the wavefront moves outward, that's circular, like this, like this, like this, with which it's moving the same speed will be the wave speed of the wave also. Okay? See this. So this, if you see again, the increment in the radius of this wavefront or this wavefront, if it's increasing with, say, if I say the radius, suppose the radius is increasing like this with the rate, say, v. So this wave motion, which is perpendicular to the circumference or the periphery points, I'm saying what? Waves motion ka direction, which is perpendicular to the peripheral points of the circular track, will be having the same speed. Okay. So it means speed of the wave is equals to the speed of the how much with which this wavefront is moving outward. You can see now. Same. A violet color arrow plus increment in the radius. It's same. Rate of increment in the radius or circular track like complete circumference is v. Rate is v, suppose. Radius increment. So same will be wave speed. Okay. So students, as per the different situations, there are different wavefronts generated. If you throw a if you throw a stone in the pond, you will see the wavefronts which are generated are circular. If you take a light source in a 3D, that is in the space like this, the wavefronts which will be coming from a light source in a space like this will be spherical wavefront, which is like this. See this. So this is a light source, and suppose the medium is homogeneous and isotropic. Homogeneous matlab symmetric, isotropic matlab on the say all of the sides you will see symmetric kind of physical and chemical changes. So from a simple light source, the wavefront which is coming is spherical wavefront. Now students, will see the revision part. Okay, pause here. So today's wave optics will study up to spherical wavefront only. Okay, now we'll start with revision of the ray optics first. So let us start with the revision of the ray optics. So this is on your screen, students. I hope it's audible. I mean, it's visible. We're starting the revision now. So wave optics may I am pausing up to where? Let's see here carefully. Wave optics may we have paused today's lecture on this topic, that is, which topic, students? That is types of wavefronts. One we have seen circular wavefront, and we have seen a little bit of the animation. Maybe it's blurred, no issues, but we have seen somewhat about, we have heard somewhat about spherical wavefront. Okay, now we'll revise some of the things in last 10 minutes, 5 minutes. Are you ready, students? Are you ready? So we'll revise now. This is very fast revision. Points are there on, it's like summary. Points are there on the slides. No need to solve the questions. What do you say? Are you ready? Yes. See, we have studied in the ray optics. Just hold on 1 second, 1 second. Sorry, we have seen laws of reflection, students. Incident ray, reflected ray, normal lie in the same plane, and this was the second law. This is revision going on. Okay, fast, quick revision. Plane mirror, then we have seen, and we have seen some things in the plane mirror, that image and the object are equidistant from the mirror, like this. Again, virtual image of the real object you're able to see there. This is the virtual image. Then we have seen spherical mirror thing. That focal length is given here as equals to r/2. Okay, and mirror equation in front of you is this: v1 by v plus 1 by u equals to 1 by f, where focus is r/2. Magnification here is given by this, that is minus v by u. This is known as magnification. This is what, students? This is magnification. Okay, so there are some questions I'll not solve now. I'll give this question as a PDF for you, okay? Because we have to revise the theory part now. So leave this thing. Yeah, we'll see just a summary because time is less. Then we have seen refractive index, which is defined as speed of light in vacuum upon speed of light in medium. Okay. Then we have seen Snell's law. This gives you that if refractive index of one medium is mu1, which is in which the light is incident, and reflective index of the other medium is mu2, where the light is getting reflected. This is angle I, this is angle R. So this will be the property which is connecting all these four things, that is mu2, mu1, I and R. Critical angle was this, that if you send a light ray from a denser medium which is having refractive index as mu into air, suppose it's a rarer medium, if the angle of refraction is 90 degree, that the light gazing the surface, so we'll say such angle of incidence in the denser medium will be critical angle. And if you increase your angle greater than the critical angle, so all the light rays will get reflected in the same denser medium. So laws of reflection will get valid here. Then we came to the reflection at spherical surface. Students, please don't make noise. Then we came at the refraction at spherical surface. If we took a refracting spherical surface, if this is mu1 on the left side and mu2 is the medium in the refracting surface, and P is the location of the object, and Q is the location of the image. So a formula is this, which connects, basically this, which connects. If suppose U is given, we have to put all these values with sign and convention, remember? Okay, this is just a summary revision. And if the object distance is given, put that distance with convention, you will get the V. if other values are given. We have also seen magnification. Remember, the magnification for this will be given by this formula if it was not written in the notes. Remember this. If they say you, what is magnification? Matlab, height of the image upon height of the object. Above the principal axis, it's positive. Sign and convention I'm writing. Below the principal axis, it's negative. Then we have reached to the lenses. If a lens may be biconvex or biconcave or whatever, with the combination of different reflecting surfaces, thin lenses are made. And suppose mu is the medium of the lens and surrounding medium is air. So focal length is given by this big formula. Okay? We have seen this is known as lens maker's formula. Whose maker formula? Lens maker's formula. Then after this, students, we have seen that lens formula was this. Suppose you are given here, this is a biconvex lens. These are just very simple, very smooth examples. Suppose this is biconvex lens. If the object is placed in front of the lens like this, so they say like this, image will be formed on this side and inverted, and this is the formula for that. M is V by U. Yaad rakhna, students, okay? Next comes the power of the lens, which is given by this, that is 1 by F. And the unit is diopter. Unit is what? Diopter. Okay, somebody will say it's a diopter. Okay, so you can use any of the pronunciation as you like. Diopter, it's diopter. Okay. Optics, you know, optics. So opter, opt, diopt. Some ways R is silent, some says diopt. You can use any of the pronunciation. Remember the meaning. And next comes a combination. Suppose two lenses are combined like this. Suppose this lens is having the focal length given by this formula, say mu minus 1 upon, say, R1 minus R2, whatever. And this is having some other focal length formula 1 by F2. So if you want the combined focal length of these two thin lenses, which is separated by a distance small d, please remember this formula. This is given by this. You have to use this formula with the sign and conventions. Every formula in this ray optics, you have to use with the sign and conventions. Remember this thing, students, always. Okay. Is it fine? Next, this thing. Okay, let us solve this one question. It's very easy. We have studied now. Total internal reflection takes place when the ray moves from a denser to a rarer medium and the angle is greater than the critical angle A, B, C, or D. What do you say? Please, GNV DIU students, Piyush, Ratnagiri students, Rangaredi, Palakad, Changlang, Harsh, please answer this. What do you say? I told you, no, total internal reflection kaise hota hai? If the ray is passing from a denser like this, gazing the surface, if it's greater than that, it will come inside. So what do you say? A, B, C, D. What is the answer? A, B, C, D. A, very good. GNV DIU students, excellent. Okay. Okay, if you're interested, next question here. A biconvex lens of focal length F forms a circular image of radius R in a focal plane. Then, what you will say? Okay, ये question में it's written biconvex lens of the focal length F forms a circular image of the radius R in focal plane. Then, what you will say? See, I am giving you this question as a homework. Okay. I want to cover the theory part also. So it's very easy. We know the focus is equals to what? Basically, in the lens, it is mu minus 1. 1 upon R minus 1 upon R2. Okay. If you keep a lens like this, and it says the image which is forming is like this. Circular image of radius R. So it can be only when the object rays are coming in such a manner to it. Okay. So you have to check this and write the answer, what it will be. Whether the focus square will be equals proportional to this or these all things. Okay. I'm giving this as a homework. Let us proceed towards the main thing now. Note this, note this. Easy, we have solved, we'll solve the questions. See, what I will do, students, for you is this. Every day we will cover some of the part of the wave optics, and remaining time, some of the time, like 15-20 minutes, we'll solve the numerical. But for now, let us complete the theoretical revision as much as we can complete. Okay, although the time is already over. So I think I need to end this session. Hold on. Okay, so tomorrow we'll see the numericals plus apparent depth thing. Okay. So here I'm going to end the class, students. Thank you so much for your attendance, and I hope the session is clear. Conclusion at the end is this: wave optics. We have started the intro, okay, and we have paused at what topic? Spherical wave. We'll continue yesterday tomorrow from this topic again. 12 p.m. What's the time? 11, 12. It's 11. Whatever. We'll see. Wavefront. And at the end, we studied ray optics somewhat, and now we skip the questions. From tomorrow, we'll see the questions also, plus remaining theory starting from the apparent depth and real depth. Okay. So students, every day we'll do 30 minutes or 25 to 30 minutes wave optics, or maybe we can extend up to 45 minutes. Yeah, that's fine. And 15-20 minutes, it depends day by day, as per your mood. 15-20 minutes every day we'll do our ray optics questions and theory revision always. So like this, both the chapters will be going. One will get complete, other will go through a thorough revision. 2 days, last 2 weeks. I mean, last 2 days of the week, ending 2 days of the week. So like this, numericals practice will give you the theoretical revision of the ray optics, plus wave optics will be completed. Slowly, small amount, step by step. Step by step, will progress. Okay. So students, this was all about today's class. Bye bye everyone. Take care. Study well. Bye bye.